Thank you. Good morning. Thank you for the introduction. And so now my current role is to lead the product management team for big data services on Google Cloud Platform. And to illustrate why I want to talk about third generation data platform, I'd like to take one example of Street View. So, when Google started to send cars around to take pictures of all the streets, there was only one goal. It was a cool feature of maps. You look at a place, it would be nice to see what the place looks like, and so let's send cars around, take pictures so we can display that. That really was the whole point of Street View. Interestingly, now those pictures have a lot more value than just the initial use case of showing you a picture of the place. We can extract a ton of information from analyzing the pictures. Example of what shops are there, street number, traffic. There's a lot more information that only became useful over time as technology improved. And when I say technology improved, obviously, there is, the labeling and the image recognition, obviously, which comes into play here. But the thing that's really transformative is not so much the raw technical capability. It's the ability to do it really cheaply, really efficiently, and at scale, which allows Google to parse every image that goes through Street View, which allows Google to take on Google Photos for free everybody's picture and help people do, find me pictures of kids on a kayak, and it will show you pictures of kids on a kayak. Just being able to do that cheaply and efficiently is really what defines what we call a third generation. And the third, the number, you can pick number you want, but we use third because we see Gen 1 as traditional on-prem data warehouse, traditional systems. Generation 2 as a move to virtualized infrastructure on cloud, getting much easier access to resources, but still in a paradigm around deploying resources, deploying cluster, more and more open source resources, Hadoop and Spark, but still in an idea that it's an IT project when you want to do big data analysis. Third generation is truly analytics as a service. It's the point where of all the tasks that you typically have to do to run a big data system, they all go away, except for the part where you bring your business expertise, where you attack the specific need that you're trying to solve, and everything else around provisioning, managing, making things reliable, securing, encrypting, monitoring, that's taken care of for you by the platform, and really enables you and gives you the efficiency, both in terms of human productivity and cost efficiency, obviously, of the infrastructure, to do the kind of thing that the Street View example showed. And so the way we came to that at Google, we've been operating that way even before Google started to do cloud. Just the way we run our services, the way we empower relatively small engineering teams. Products like Gmail, like that touch a large number of people, have surprisingly small engineering team because they live in a world where the infrastructure is taken care of for them, and they can really focus on building large-scale, cost-efficient, productive systems. And so as we were doing that, we were publishing papers, describing the work, and at that point just publishing the paper and moving on to the next thing, not really following through because we just had something else to work on. And so what happened is that people outside Google, companies like Yahoo and Facebook and others, would take those papers and re-implement the technology based on the description. More famously, HDFS based on Google File System, MapReduce based on the Google MapReduce paper, Dremel, so Dremel has a storage part which became used by Apache Parquet, and the query part which is Drill, HBase based on Bigtable, etc. And that was great, and those are great services and great tools that bring those patterns to the world. Lately, and by lately I mean 3-4 years now, so not that recent, we've changed the engagement model in the sense that we still publish papers, and actually more and more, but when we do that, we also open source the programming model, the SDK, like TensorFlow recently, like Apache Beam, which I'll describe in a bit more detail, and we also expose the actual underlying Google services that we use and that are the services mapping these technologies. And so now, obviously we share the ideas, we share the code, and we share access to the actual optimized infrastructure. And so in practice, the way that presents itself and can be consumed by users of Google Cloud Platform is kind of this kind of overview of the various services. And I'm not going to describe every one of them. The point here is that across the life cycle of the data, from the point of capture, processing or pre-processing, storage, analysis, there are fully managed services that provide that level of efficiency to users to really focus on building the application. And so one example to illustrate that on the upper left is Cloud PubSub. So PubSub, publish, subscribe. The pattern itself, there's nothing new, nothing original. We all know how it works. Topic, you subscribe to a topic, you publish to a topic. So the pattern is perfectly standard and typical. The part that's unique is the operating model, meaning that to do this, all you have to do is you make one API call to say, create a topic, and the topic is created. The topic is a first-class cloud resource. You can put ACLs on it, who can post to it, who can subscribe, and that's it, you're done. If there is no traffic, that topic costs you zero. It just sits there doing nothing, and you don't have stranded infrastructure just waiting. If you start to have traffic, we'll scale it up for you. We'll reliably deliver messages, taking care of all the reliability, encryption of the data. By the time a message is accepted, by the time your request to post is accepted, you get an ACK back. The message has already been replicated on Google Fiber Network across geographies, across data centers, providing reliability. And so that's the interesting part here. What this illustrates is a very typical programming model, but a very unique operating model for that service to capture. Spotify uses that to capture all the events on the Spotify players, through that song starts, song ends, all those things, and a lot more. Flows is captured that way because that's really the way to leverage Google's network presence and ingestion capability. Typically, downstream from PubSub, one of the things that people often use is stream processing pipelines to process events as they arrive. And one product there is Cloud Data Flow, which this one, unlike PubSub, is actually, sorry about that. Can you close the update window? Safari or something Safari wants to update itself, always at the right time. Okay, that's not even there. So while the slide comes back up, thank you very much. The part that's unique about data flow is that in addition to the programming model itself is quite unique. So both the programming model as well as the operating model in that case. The programming model is unique because it unifies batch and stream processing. And the way to do that is, the first thing is to realize that there is really two times that are involved when you do stream processing. There is the event time, when the thing actually happened, when something happened in the game or some device captured something. And there is the processing time on the y-axis, which is when your pipeline actually sees the event. And if you assume the two are the same, then you're going to get some weird results, because in reality, events always arrive with delays, sometimes milliseconds, sometimes minutes or hours, if your device, if you're on a plane and your device loses connectivity. In some use cases, assuming the two are the same is okay. Most of the time, it's not. And so once you recognize that they're not the same, and so for example, here we have event number 3 arrived on the processing pipeline very close to the time it actually happened. Event number 9 took a really long time to arrive. How do you deal with that? So the way you deal with that with data flow, and actually with Apache Beam, and I'll describe what I mean by that, is to really split your logic into 4 different pieces of your pipeline that do not overlap, to allow you to really compartmentalize how you describe your pipeline. So first, there is the what. What do you want to do? In this case, I take a very simple example. I have a bunch of people like playing a game, for example, by team. I want to group them by team, and I want to sum all the points that they earn. Very simple. I'm just doing a sum. Obviously, in real life, this is where the actual logic goes that describe what you want to do. But that logic is written in an ideal world in which every event arrives right away in the right order. And so you can write really clean logic based on the actual event time. And the way it gets it, at that point, all you do, you're saying you want to sum things. So what it's going to do, it's just going to sum everything. Nothing fancy, but it's a very clean, simple way to describe your logic. The next thing is, okay, but this is streaming now. I don't just want a sum of everything over the entire time period. I want to have windows and get, in this case, my point coins by window. And so separately, without having to pull you the logic of the what, you just say how you want things split, by sessions, if you're looking at web traffic, by sliding window, by fixed window. And you can change that without ever changing your actual business logic. And so in this case, I've asked for 2-minute windows. And so the addition happens in 2-minute window. But at this point, I'm still only calculating, I'm still in batch mode. I'm still only calculating when all my events are here. I'm just windowing my results. The next thing, and that's where that's where we get into real streaming mode, is the ability to what we call trigger, which is to calculate the value for a given window, at some point early, to not wait forever to trigger. And so the easiest way to do that is actually to tell Google, you figure out when the data is there for my window. And Google maintains a watermark based on heuristics, based on our experience of understanding delays in arrival, to try to optimize when we can trigger. And it's not perfect. There's no way to guarantee a late event is not going to happen. So in this case, we've missed this late event. But it gives you a real-time approximation of your results and then you can start, we call emitting the results on the fly. Now, what we want is actually better than that. We want something that provides correctness. So by the time, we want something that provides the same result by the time I get to this moment, as if I had done nothing and waited until this point and done a batch calculation. And that's how you get correctness. That's how you avoid having to do stream and batch, stream for fast results, batch for accuracy. And the way you do that is because the programming model, again, in a separate section, which doesn't pull you the rest of your logic, allows you to define rules for early triggering, if you want to build up your results often, rules for handling late events. Do you want to discard them? That's fine, that's an option. Do you want to update your results? Do you want to retract and update? And so the semantics are there, which in the end allows you to compose a pipeline that provides correct result, the exact same results that a batch mode pipeline would have done. And by the way, you can also run it in batch if you're processing historical data or if your data arrives in batch. And so that's the programming model. I called it a data flow programming model. That's the name of the paper. But then when we submitted it to Apache, obviously they wanted to use a neutral name. That wasn't a name used commercially. So we used the word data flow as our cloud product. And so the open source name for this is Apache Beam. And it's easy to remember because the B of Beam is batch and the EM is stream. And so really the name says what the programming model does. It unifies batch and stream. It came from Google. It came from Dataflow. There's nothing in it that's Google specific. In Apache as an SDK. And actually, it works on many different runners. And so people from Cloudera joined us to write a Spark runner. So you can run Beam pipeline on Spark. People from Data Artisan contributed a Flink runner, same thing to run Beam on Flink. The blue logo is Google Cloud Dataflow, which is if you want to run that on Google's infrastructure. There are runners in the work for Apache Apex, for Gear Pump, and more runners. And so it provides, in addition to the niceness of the programming model, it also provides a layer of portability to whatever is today the right runtime for you, and more importantly, whatever is going to be the right runtime in 2 or 3 years. So you don't have to keep porting things from MapReduce to Spark, from Spark to Flink, or nobody knows, frankly, what the best runtime is going to be in 3 years. And so that gives you that level of portability for your applications or for the tools that you want to build that generate pipeline. If you choose to run on Google, that Apache Beam pipeline, then we're back to the discussion around fully managed auto-optimized services. What you get is that you're not deploying a cluster and running pipeline in the cluster. What's actually happening is you're just sending us a pipeline. Say, please run that pipeline for me. And Google Cloud automatically creates resources, auto-scales. We bring all of the optimizations that we've done internally around reclaiming work from slow workers, shuffling, a lot of the things that we've learned over 15 years. We bring those optimizations to work for you in a fully managed system where you have nothing to manage. Just deploy a pipeline and we'll run it for you. So that's Dataflow. Another service I want to mention is BigQuery, which is our data warehouse. And BigQuery here, I show it in 2 places because you really can think of it as both a storage system and a processing system. And as a storage system, it's actually not tied just to the BigQuery processing system. You can access it through all the other processing systems. From Sorry, that's a build-up. The way to think about it, again, fully managed. And so what does it mean? It means the only thing you have to do is, one, bring your data. You can do a load job. You can load data for free, or you can stream data, event by event, and you can ingest up to 100,000 rows per table per second. However, you bring your data, and then you submit a SQL query. That's all you have to do. You don't have a cluster sitting there. You don't have to pre-provision how much storage you need. You pay exactly for the number of bytes that you use in storage, and you pay for the queries that you run. And because it's such a large, optimized multi-tenant system, when you run your query, you may get thousands of workers for 5 seconds running your query. So you get great performance at a very reasonable cost because you're only paying for what you're using. One thing, so it's been out for a while and very popular, especially around startups. I talk about Spotify and companies like that. As far as enterprise usage, there were some really happy users, but we also had people coming to us saying that they were getting some friction with the way they were used to operating. One of them being the biggest one, probably being that the on-demand nature of pricing. Paying per query is very powerful. It actually is very cost efficient and gives you a lot of flexibility. It's also hard to predict when you have a monthly budget. So we now offer a monthly rate. You pay the same rate, you send as many queries as you want, and then you can use a certain capacity that you've paid for. And it's a more traditional way to consume. It's still the same underlying engine. We've also released ANSI-compatible SQL. The previous version had some specificities, so now it can be compatible. And things like ODBC connectors, things like ability to do updates. It used to be append only. Now you can do updates and deletes. Integration with IAM, things like that really make it fit well into a traditional data warehouse environment while still keeping kind of the raw power of the underlying engine. And then finally, another service, and that's where it becomes interesting, is that I've talked a lot about cloud-native services, which in our case happen to be the services we built for Google itself. But there is a lot of value and useful tools, obviously, in the big data ecosystem. And when that's the right tool for the job, that's the tool you should be running on Google Cloud as well. And so we've created a product called DataProc, which is a managed Spark and Hadoop clusters. And so it will spin up a cluster for you in about 90 seconds. You can get hundreds of nodes. From the time you say, give me a cluster, to the time you can start using them, that's about 90 seconds. And we charge by the minute. And that cluster has access to all the data stored at Google, whether on Google Cloud Storage, which is our S3-like object store, whether on BigQuery, whether in Bigtable. So that cluster comes up. You don't have to copy data into it. You just have the cluster. 90 seconds later, you run a job. You read from somewhere, you write to somewhere, and if you want, you can shut down the cluster. And you've paid for 15 minutes, 25 minutes, exactly what you need. So it's a very flexible way. It's a very cloud-like way to use open source, but it is standard Hadoop and Spark with all the libraries and the vast ecosystem of tools. And so you can really mix and match those Hadoop tools or Hadoop and Spark tools with the cloud-native services. And so to illustrate the value of this very dynamic model of using Hadoop and Spark, which is very different from the traditional on-prem model of having a long-lived cluster, some people at O'Reilly actually did a comparison. So that's not ours, that's from O'Reilly. I think the URL is there. And so they run two jobs, a relatively small one comparing EMR on Amazon to DataProc on Google. And so on the similar clusters, they looked at the cost of running a small job and a large job, and small, like smallish, it's actually not small, 57 million rows. And so it's because of, frankly, it's a lower price to start with, of the per minute billing, of the efficiency, you can see the big price difference for the small one, but also for the larger one. And that's really, it's the same Hadoop and Spark bits, whether on Amazon or on Google. The thing that's different is A, the infrastructure, the network, but B, the flexibility of short-lived clusters. So that's it. That's the quick overview I wanted to give. And really the point here was that across the platform, across the life cycle of the data, you should be able to rely on cloud-native services, which are already managed for you, optimized for you. And when the only thing you have to do is really bring your business expertise and use the most advanced tools to implement your analytics, all the way from traditional data warehousing to using Dataflow, Hadoop Spark, all the way to machine learning. One thing I haven't mentioned also is that we're making Google's machine learning training services based on TensorFlow, which we've also open sourced. That's another example of a cloud-native service where we'll train your model for you and run your predictions for you. So thank you very much.